connection between these. And I touched on some of those connections yesterday, and we'll see some more of them today. So this talk concerns, as I say, the application of twistor methods in the context of self-dual gravity, and it's based on a series of papers, two from last year. One was written with Atul Sharma, who's at Harvard, and Dave Skinner, who's at Cambridge, and a paper I wrote myself, which followed on from that. And then this year, we have a paper that came out very recently, again with Dave and with his student Simon. Okay. So first, before perhaps explaining what I precisely mean by self-dual gravity, I want to just motivate why I should think about something like this at all. So general relativity in 4 dimensions is, of course, very interesting. It describes the gravitational sector of our world, at least at energy scales that we can experience. But unfortunately, it's a very complicated theory. For example, it's non-renormalizable, and its amplitudes are difficult to compute. They have a lot of rich structure. Self-dual gravity, on the other hand, is a considerably less interesting theory, but it's also orders of magnitude simpler. It's classically integrable, it's one loop exact, and it's finite. But nonetheless, I think we'll find that there are some interesting things we can say about it. Crucially, it has some of the essential features that full general relativity has. It's a 4-dimensional theory of gravity, and it has 2 propagating degrees of freedom. It has a positive and a negative helicity graviton, just like Einstein gravity. And finally, we can deform away from the self-dual sector, and that's the real motivation for thinking about it. And we can leverage the fact that the self-dual sector is so simple to understand some things about full general relativity. So what exactly do I mean by self-dual gravity? I'm going to be largely working in Euclidean signature or in split signature. That's because the self-duality equations only make sense, are only compatible with reality conditions in those signatures because the Hodge-Star operator has plus and minus 1 eigenvalues, whereas in Lorentzian signature, it's got plus or minus I eigenvalues. When we do certain computations using twistor, computations, they very naturally analytically continue to all signatures. So if you compute an amplitude, for example, what you'll find if it's really come from a twistorial theory, it'll be some rational object, a meromorphic object, and then you can very easily Wick rotate and you can interpret it in Lorentzian signature. But really, for the theories to make sense, oh, okay, that's the message in the chat. We should either be in Euclidean or split signature, plus, plus, minus, minus. And for now, I'm going to be in Euclidean signature, all plus. So a metric is self-dual Ricci flat if its Weyl tensor is self-dual and if its Ricci tensor vanishes. So of course, the vanishing of the Ricci tensor is precisely the vacuum Einstein equation with 0 cosmological constant. And so we have this extra condition, which is the self-duality of the Weyl tensor. So this is extra. In the Riemannian signature, it turns out in 4 dimensions, these conditions are equivalent to the metric being hyperkähler. So that means you've got a sphere's worth of complex structures on the manifold M, which are compatible in a certain sense. A nice way of rewriting these equations is by splitting our metric into Vierbeins. So here, I hope this isn't too confusing. An alpha index is a left-handed spinor index, and alpha dot index is a right-handed spinor index. When there are 2 of them together, that's just the same as a Minkowski index. And then this circle dot just means I'm taking the symmetric product of forms to get a metric, as opposed to the wedge product. It turns out that the self-dual Ricci flat condition above can then be written in this rather compact form. So the closure of this product of wedge product of the Vierbeins. Before I go on, I just want to very quickly say, okay, sometimes I might call these metrics self-dual Einstein. Whenever I say that, I mean vanishing cosmological constant. Everything I say in this talk will have vanishing cosmological constant. So if I do say self-dual Einstein, I hope that that's not confusing. I hope that should be clear what I mean by that. So I expect this equation might be a little bit unfamiliar, but I think it's easier to understand how to get to the self-dual theory, starting with an action for full general relativity. So there are a number of different actions for GR. I'm going to look at starting with something called the self-dual Palatini action. So this is a first order action for general relativity. So it depends on Vierbeins and it depends on a spin connection. And it's called the self-dual Palatini action. So I should emphasize this is not an action yet for self-dual gravity. This is an action for full gravity, at least perturbatively. The remarkable thing about this action is it only depends on the anti-self-dual part of the spin connection. And it's a really remarkable fact that you can write 4D Einstein gravity in this form in a way that where only the anti-self-dual part of the spin connection is required. And that's why this was given the name self-dual. So this is not quite equivalent to the standard tetratic Palatini action. It differs by a topological term, the Near-Yang term. But in perturbation theory, that topological term doesn't matter, and it's equivalent. So to get to self-dual gravity, we linearize the anti-self-dual part of the theory. So if you went to the talk yesterday, that's how we get from the first order formulation of Yang-Mills to self-dual Yang-Mills. You remove the B squared term, where B is the anti-self-dual field. In the same way, here we're going to take the anti-self-dual interaction, which is this gamma squared term, and we're going to throw it away. This might seem a little bit of a strange thing to do. It almost feels like this is the analog of F self-dual Yang-Mills, but actually it's really playing the role of B. When we do that, we're left with this action for self-dual gravity, which is just the two Vierbeins wedged against D of what was originally the anti-self-dual spin connection, which has now been sort of linearized, and it now just acts as a Lagrange multiplier. If we integrate it out, what we'll find is we impose the self-dual vacuum Einstein equations. Perturbing around flat space, we just take our Vierbeins to be the standard Vierbeins of flat space plus some perturbation. We can use this to think of self-dual gravity as a perturbative quantum field theory. And so this is what I mean by self-dual gravity. Oh, is there another message in the chat? Yes, I think there's a link in the chat. So there's a question in the chat. There's a link in the chat as well to the YouTube video of the talk yesterday. I should say that it shouldn't be essential. It's not a prerequisite for today's talk. I'm just might mention some things that I said there. I'll try not to do that too much. Okay. Ooh. Great. So I argued yesterday, and the view I will take today is that for a 4D theory to be integrable, it really means it has a twistor formulation, that you can lift it up to twistor space in a consistent way. And we can do that for self-dual gravity. And the basis of that is Penrose's nonlinear graviton construction. So I mentioned a few of the Penrose correspondences and the Ward correspondence yesterday. Today, I'm going to talk about a very specific example, which is a little bit more refined than the ones I mentioned yesterday. So it's a correspondence between 4D Riemannian manifolds with self-dual Ricci flat metric and three-dimensional complex manifolds called twistor spaces. And it's really this Ricci flat condition which gives me some of these extra conditions. So if it was just self-dual Weil tensor, then it would admit then we would have a three-dimensional complex twistor space, but only if it's Ricci flat do we have a holomorphic vibration over the P1. And you should think of this, I mentioned a moment ago, that this self-dual Ricci flat condition in 4 dimensions is equivalent to being hyperkähler. This CP1 is really the CP1 of possible complex structures on your hyperkähler manifold. So as you can think of your twistor space fibering over that P1, and as you move around, and the fibers you can think of as copies of your hyperkähler manifold in a particular complex structure, and as I move around, I vary the complex structure. And then crucially, on those fibers, we have an O2 valued symplectic form. And all that O2 means is that as I move around this P1, these symplectic forms have some weight. They transform in a non-trivial line bundle. Yeah, so then we call this three-dimensional complex manifold the twistor space of M. Points in our space-time, really in the complexification of the space-time, are rational curves in the twistor space. And those that correspond to the Riemannian slice of this complexification are then fixed by a certain anti-holomorphic involution. And I won't say too much about that, but again, I don't want to focus too much on reality conditions, but I guess this is important. So I discussed yesterday how in flat space, having this anti-holomorphic involution allows you to construct a holomorphic fibration of your twistor space over your space-time in if you're in Riemannian signature. And so what that allows you to do is it allows you to think of this twistor space as being just a sphere bundle over the space-time, and then to go from twistor space to your space-time, you just do a Kaluza-Klein reduction. But the funny thing is that all these theories on twistor space have some enhanced gauge symmetry, which means that there are no higher Kaluza-Klein modes. We just get sort of massless degrees of freedom in the 4D space-time. So an example of this is the twistor space of flat space. So this is denoted PT. It's just the bundle O1 plus O1 over CP1. And certainly flat space is self-dual Ricci flat. And as we see, the twistor space fibers holomorphically over CP1, and it has a symplectic form of on the fibers. So it's just, I'm going to use the coordinates V alpha dot on the fibers, where alpha dot goes between 0 and 1. That just means that this is sort of transforming as a right-handed spinner. And I'm going to use the coordinate Z on the base. And then our symplectic forms on the fibers of this are just dv0 dot wedge dv1 dot. And it's precisely because those V's are living in some non-trivial vector bundle that this symplectic form has the weight that we saw on the previous slide. I'm going to be looking at perturbative quantum field theory. So that means I want to view my space-time as being a deformation of flat space. And to do that on twistor space, I just need to view this curved twistor space as a deformation of the flat twistor space. We can encode a deformation of an almost complex structure on twistor space in a deformed covariant Dolbeau operator. So I'm going to write my Dolbeau operator on this curved PT as the d-bar operator on the PT of flat space plus some correction. And that correction is encoded in is encoded in what's called a Beltrami differential. So Beltrami differential is a 0-1 form with values in the tangent bundle. And this describes a deformation of the almost complex structure. There's one thing I just want to be a little bit careful about. I've written this d-bar on this, the twistor space of flat space is just sort of the standard Dolbeau operator, but it's not a completely trivial Dolbeau operator because twistor space is not just C3. Already the twistor space of flat space is non-trivial as a complex manifold. So it's important to remember that this d-bar is already sort of non-trivial, and then we're adding something to it, which is potentially going to be more non-trivial, more complicated. I said that this defines an almost complex structure. To get an honest complex structure, we need it to be integrable, and the integrability is encoded in the vanishing of the Nienhaus tensor, which is just this d-bar of the Beltrami plus the commutator, which is the commutator of vector fields. But I'm interested in deformations of the metricon space-time, which are self-dual Ricci flat. And we said that on twistor space, those don't just correspond to generic complex structure deformations, they correspond to complex structure deformations which preserve a fibration over P1 and which have this O2 valued symplectic form. And so to enforce that condition on the complex structure deformation determined by this Beltrami differential, I'm going to require its Hamiltonian with respect to the complex structure on the flat twistor space. So the symplectic form determines a Poisson bracket. That Poisson bracket has weight because the symplectic form had weight. So the symplectic form was valued in O2. The corresponding Poisson bracket is going to be valued in O-2. And then I'm just going to require that this Beltrami differential is Hamiltonian for some 0-1 form, but I want my Beltrami differential to be weightless. I want it to just be an honest, I don't want it to transform in some funny bundle over the P1. And so what that means is I have to twist this Hamiltonian H by the bundle O2 to compensate the twisting of the bracket. And then the V is just an ordinary honest Beltrami differential. That's going to determine Hamiltonian almost complex structure deformation. Integrability of that complex structure is then imposed, follows as a consequence of the vanishing of this object, this curvature-like object that I called T of H. So it's very similar to the kind of curvature we'd write down for, say, a partial connection on a G bundle. The difference is that this isn't Lie algebra valued now. It takes values in some line bundle, and the term which would usually have been a commutator term is now a Poisson bracket term. We can then write down an action, a twistor action for self-dual gravity, which just imposes this condition with a Lagrange multiplier. And the theory, we call it Poisson BF theory, because it's like a holomorphic BF theory, but the only difference is instead of having a commutator, it's got a Poisson bracket. And this is the formula for it. It was suggested by Lionel Mason and Moss and Wolf in 2009. And this Lagrange multiplier field G, it just has whatever weights and lives in whatever spaces it needs to pair appropriately with T. It's possible to show that this Poisson BF theory is actually classically equivalent to the action I wrote down a few slides ago for self-dual gravity. But I should say, yesterday I sketched some of these reductions from twistor actions to space-time actions very explicitly. That's much harder to do in gravity. So it can be done. Atul Sharma did it for this action first in 2021. And then in our paper together with Dave, we presented another slightly different reduction, which also shows that you land on self-dual gravity. But these are very technical computations, actually. It's not, for some reason, the gravitational case is just an order of magnitude more difficult, I think, than the gauge case. So just like the self-dual Yang-Mills equations are integrable, the equations of motion of self-dual gravity are integrable. And in a sense, this twistor construction is making that integrability manifest. It's taking this very complicated set of differential equations on space-time, and it's recasting it in terms of some kind of algebraic data. You just have to construct a certain complex, complex manifold with certain structures. So in a sense, that's formally, it's solved. I mean, of course, in practice, it can be quite hard to construct twistor spaces, but in principle, there's it's a formal solution to the problem. So when I say something's integrable, what I mean by that is that it has an infinite dimensional hidden symmetry group. And one of the reasons this is so interesting at the moment is because this infinite dimensional hidden symmetry group turns out to be exactly the same algebra that people get by thinking about positive helicity asymptotic symmetries that you get from soft theorems in general relativity. To see exactly what this is, I'm going to use this neat trick where we think of it as the universal holomorphic surface defect living on a twistor line on the twistor space. And again, this is really using the fact that having this twistor description makes this hidden symmetry manifest. So first we write down the most general coupling between some theory living on a twistor line. So this is the twistor line over a point in our space-time, and the bulk Poisson BF theory. So again, you should think of this as kind of a generalization of a Wilson line in, say, Schoen-Simons theory. So in Schoen-Simons theory, I would pair the connection, which would be the analog of H here, with some Lie algebra generator, which would be the analog of WOMN. I then impose a BRST invariance on that line operator, and what that would tell me is that those Lie algebra generators have the correct, the expected commutators. Here, we're going to do a very similar thing, except now this is a theory living on a two-dimensional space, so these objects depend on a holomorphic coordinate Z, and we can couple not just to the field H, but also its holomorphic derivatives, and that's because we couldn't couple to anti-holomorphic derivatives because those are exacting BRST cohomology. And for example, in a topological theory, we wouldn't be able to couple to derivatives in any direction because they'd all be exact. But here, these holomorphic directions are non-exact, and so it's natural to include them as possible couplings. We also have this Lagrange multiplier field, and it's important to include the possibility that our defect also couples to that. So that's what these W tildes are. And then we just require that the surface defect is BRST invariant. So at tree level, there are two diagrams with two external legs, two external H legs, which contribute, and they are the following ones. It's always these two diagrams, or at least in most examples, it's these two diagrams that give you the tree level OPEs or commutators. And the BRST variation of this first diagram just picks out the residue of taking this point around this point, remembering that LX is not, it's a Riemann sphere. So this is really a two-dimensional space, this LX. And what we find is the residue of taking this object around that object, this W around that W, has to be related to basically some structure constants coming from the Poisson bracket and the W there. And what that means is that you have to have the following OPEs. So these P's and these Q's, these are non-negative integers because those pair with holomorphic derivatives of our field H. And so we have to have non-negative number of derivatives, and so these P's and Q's are non-negative. Yeah, so this should be, hopefully this is clear. So I'm going to refer to this as the hidden symmetry algebra or celestial chiral algebra of soft-dual gravity, and I'm sometimes going to write it as SDGR, sort of preempting some kind of connection to W algebras. And then I'm also going to write this as L of ham-c squared. Let me explain precisely what I mean by that. The idea is that these structure constants, they might seem a little complicated, but they're actually some very, very, very simple structure constants. So ham-c squared, this is Hamiltonian vector fields on holomorphic Hamiltonian vector fields on C squared with its standard symplectic structure. This is the same as just the complexified phase space of a classical particle in one dimension. So what I mean by that is polynomials in a position variable x and a momentum variable p with the standard Poisson bracket. So this is probably one of the simplest examples of a Lie algebra one can imagine. It's one of the first ones anyone will come across. When studying physics, they probably wouldn't recognize that it was a Lie algebra at first, but honestly, this is probably the most natural, one of the most natural things one can write down. And this ham-c squared, the structure constants of ham-c squared are precisely this PS minus QR. So I should think here of this WPQ as being corresponding to the generator x to the power p and p to the power q in this phase space. And then if I do the same for the second variable and I took a commutator, I'd get this numerator. The L then just means that I take the Lie algebra of loops, or the loop algebra of ham-c squared. And what that means is that now everything just depends on a z, and there's a simple pole. It turns into a vertex algebra. Actually, I should be a little bit careful there. Vertex algebra has more information than this. It also has a vacuum module, but yeah, we can think of it as sort of taking our Lie algebra and somehow constructing some kind of vertex algebra from it. So these are the OPEs of the W's. I also introduced these tilde W states, which couple to G, and they're just going to transform in the adjoint of WSDGR. So they have the following OPEs. So they get hit by a W, and they just give a W name. They just reproduce a W tilde. So W tilde goes W tilde, and they have trivial OPEs among themselves. So the W tilde OPE is always 0. Okay, so I now want to flesh out precisely what the connection is to celestial holography. And the celestial program is really came about by thinking about soft theorems and amplitudes. And so I want to sort of recast these structure constants and interpret them in terms of amplitudes. So to do that, I first want to take this inhomogeneous coordinate z, which if you recall was an inhomogeneous coordinate on a twistor line. And I'm going to reinterpret it in terms of some kind of homogeneous variable lambda. And this CP1, you can think of it as the celestial sphere of space-time, and it transforms under left-handed rotations. The left-handed rotations would act on Z as a Mobius map, and on lambda, they just act in a fundamental. Then I'm going to take these generators, WMN, that I mentioned before, and I'm going to introduce some auxiliary variables, lambda tilde 0 dot and lambda tilde 1 dot. And these have suggestively got 0 dot and 1 dot indices to indicate that they're actually going to transform under right-handed rotations. And I'm going to organize them into this generating function, which I now think of as depending on this lambda tilde spinner, the right-handed spinner lambda tilde, and a left-handed spinner lambda. So sometimes people call these WMN states soft modes, because somehow this corresponds to expanding in some kind of energy. And then this is a hard mode, because we've summed up all the soft modes together. So arbitrarily high numbers of soft modes. We can then interpret lambda and lambda tilde as spinor helicity variables and form a complexified null momentum. Of course, if we're really in Euclidean signature, we can't have null momenta that are non-vanishing, and so we really need to think of this as a complexified momentum. But that's precisely what this is. And We can rewrite the OPE in this kind of slightly more fancy language, and it takes the following form. So here, this angle 1, 2 just comes from taking the SL2C invariant combination of two lambda variables, a lambda1 and a lambda2. And if you express it inhomogeneously, it's just going to be a Z1 minus Z2. And the square brackets, we just take the SL2C invariant combination of the tilde variables, contract them into an epsilon symbol. This object tau here isn't important. I just wanted to make sure I didn't write down anything wrong. This is essential just to absorb various weights, make sure everything's transforming in the correct bundle. If you work in inhomogeneous coordinates, you'll find that this disappears, and the dependence of the OPE on this object is irrelevant. The singular part of the OBE, which is what we really care about, is independent of this thing. I just wanted to make sure I didn't write something that's wrong. The purpose for writing this in this slightly more complicated way is to extract this combination, this minus square brackets over angle brackets. And members of the audience who've got some familiarity with graviton amplitudes might recognize what that is. It's what's called the tree graviton splitting amplitude. So if you have some tree graviton amplitude, and we have two positive external Listy legs, so I want to imagine that this diagram on the slide is just some very, very small part of a very large Feynman diagram contributing to a tree graviton amplitude. And I want to take two positive holistic external gravitons, and I'm going to take their momenta, this P1 and P2, to become collinear. When I do that, the amplitude will in general have a singularity, and at tree level, that singularity has to come from a diagram of this type. There has to be some propagator connected by a 3-point vertex to the external momenta, which is going on shell, which is blowing up. And the singularity of an amplitude in this limit is universal. It doesn't depend what amplitudes I'm looking at, in a sense, because this part of the diagram, the singularity has to come from a diagram of this type. And it turns out that if you evaluate what this is, it's precisely this minus squares over angles. So in this way, the structure constants of this hidden symmetry algebra are encoding this collinear behavior around amplitudes. Okay, but would be a little bit surprising if somehow the self-dual theory of gravity knew something about all the amplitudes in full Einstein gravity. So we need to make a precise statement about what exactly this hidden symmetry of the self-dual theory is telling us about. So for those of you who were at the talk yesterday, I explained how the celestial chiral algebra of self-dual Yang-Mills is telling us about the universal collinear singularities of amplitudes in the presence of local operators. So it's singularities of amplitudes in self-dual Yang-Mills in the presence of a local operator in that theory. And you can sort of use a single insertion of an operator to sort of move you one step away from the self-dual theory. And those go by a name called form factors. Unfortunately, in gravity, life isn't so easy. We'd really like to make a statement analogous to that this chiral algebra is telling us about the collinear singularities of amplitudes in the presence of local operators in gravity. Of course, there are no local operators in gravitational theories, so that can't be quite what the algebra is describing. But there's a very closely related notion, which is a first order deformation. So a first order deformation is, instead of inserting a local operator evaluated at some point x, I'm going to insert the integral of a local operator. And this saves us in gravity because it's no longer necessary for this object to actually be BRST, by which I mean diffeomorphism invariant. It just needs to be BRST invariant modulo Durand exact things. And in fact, there's a very precise sense in which objects of this type can be thought of as local operators. So having a condition like this condition that, I seem to be unable to highlight it. Okay. This condition that the BRST variation of an operator is exact for another operator, we can chain it. We can chain this process. So take BRST variation, then the BRST variation of O prime has to be exact. And this allows us to take, I guess, what is a four-form operator, which is the thing we're integrating, and turn it into a local operator, but with higher ghost number. So these really are the natural analogues of local operators in our gravitational theory. They're first-order deformations. So a very natural example of a first order deformation is the one that takes us from self-dual gravity to full Einstein gravity. So if you remember, there was this term I threw away from the self-dual Palatini action to get to self-dual gravity. To get back to Einstein gravity, I just need to add this in. But of course, I really need to introduce it in the exponential. And I'm only, in these first order deformations, I'm only allowed to introduce it once inside the path integral. So this is, again, it's taking me one step away from self-duality. If I add this operator, it's taking me one step away from self-duality into full Einstein gravity, but it certainly can't take me all the way because I'd have to introduce it multiple times, and then life gets more complicated. My claim is that this hidden symmetry algebra is really capturing the collinear singularities of tree graviton amplitudes in the presence of deformations of this type. And I say tree there because at the quantum level, things get a little bit more complicated, which we'll come on to shortly. So let me just explain exactly why that works. The idea is that the only non-vanishing tree amplitudes in self-dual gravity are the 3-point vertices. And it's just a plus to minus vertex. This is not completely obvious to see. There are trees you can draw, which have got endpoints, but it turns out they all vanish. You can show that they're all 0. And so the only non-vanishing amplitudes are the 3-point vertices. So then if I consider an amplitude in a first order deformation of self-dual gravity, and then I take the momenta on 2 external gravitons to become collinear, the only way I can get a non-vanishing answer is if there's a propagator, which is becoming singular, which is going on shell. That's the only thing that can give me a singularity. And this propagator has to connect some non-vanishing tree amplitude to some other non-vanishing tree amplitude. But the only ones I've got in the self-dual theory are the 3-point vertices. And so I'm always going to end up, and on one side of the propagator, I have to end up with something, which is only on one side can I introduce the local operator O. Only on one side can I insert this deformation. And so what that means is the collinear singularities are always going to be captured by just the vertices of the self-dual theory. And this is how this hidden symmetry algebra can tell you something about any deformation away, any first order deformation away from the self-dual sector. Because the collinear singularities are universal. They don't depend on what deformation I do. And it's because of this remarkable property that there are essentially no amplitudes, at least in tree level, at self-dual gravity. Okay, now I want to move on and talk about quantum corrections. So requiring the BRST variation of the defect at one loop forces some changes to the operator products. So there's a new diagram which can contribute. I've got this line X here as a twister line. There's now a Feynman diagram of this box type. And if I compute the BRST variation, I'll see that I need to correct the operator products. And you can do that very explicitly. I do this in the paper I wrote. And what you'll find is that here I've written here probably the simplest correction. It necessitates many more corrections to this. In fact, it necessitates even more corrections to this operator product I've written here. But I think this is the first one which captures, it's the first OPE where you see this double pole appearing. And that double pole is really important, and we're going to be able to understand physically what this double pole in the algebra corresponds to in terms of amplitudes. I've highlighted this coefficient of 2 over 5 pi squared because it's going to reappear later. This shows up when thinking about amplitudes. And I've added one example extra term. As I said, there are more simple poles. I added this one just to illustrate the fact that you can get normal ordered products. So what this means is that we've the mode algebra of this vertex algebra is being deformed, is not being deformed as a Lie algebra. It's really been deformed as an associative algebra. So you can think of this as a kind of quantum group. Well, okay. What we'll find is actually this doesn't define a consistent chiral vertex algebra. We'll have to do some modifications to get something consistent. But these kind of deformations, they're moving us away from just ordinary Lie algebras. So that's the thing I wanted to emphasize with this term. And as I say, there are more simple poles even in this example APE, but I didn't want to. I mean, they're not very enlightening. So I just wanted to give you the simplest ones. Okay, so I gave you this interpretation of sort of the structure constants of this hidden symmetry algebra in terms of amplitudes. So how should I interpret the fact that the chiral algebra seems to be corrected? Well, it seems the natural interpretation is that somehow the collinear behavior, the collinear singularities that you get in one loop graviton amplitudes should be different from those that you just see in tree amplitudes. There should be some modification. Surprisingly, that isn't true. So it's a remarkable fact that there are no one loop splitting amplitudes in gravity. But the thing that we're seeing here is the difference between sort of that result and what we're seeing here is that there are no one loop splitting amplitudes in the true collinear limit. So the true collinear limit means that we take one of the momenta and we take it to be proportional to the other momenta. This seems to make sense. That's what collinear means. But if you remember, these are null momenta. That means that they can be expressed in terms of left-handed and right-handed spinor helicity variables. And now I can imagine taking the left-handed spinor helicity variables to become collinear while leaving the right-handed ones distinct. And that's what I'm going to call the holomorphic collinear limit. Now, you might notice that I'm certainly not allowed to do this in Lorentzian signature because lambda and lambda tilde are in Lorentzian signature. But in split signature, or if I'm just working in a complexified world where which I am in sort of Euclidean signature, then I can take this limit and I can capture the singularity. And it turns out that these singularities are modified. The collinear singularities in one loop amplitudes are modified in this limit. And in fact, I mean, I don't think this point has perhaps been emphasized enough in the literature. It only shows up when some rather technical recursion calculations of loop graviton amplitudes. But it seems like a really important feature of these amplitudes that they can acquire these double poles. It's also worth mentioning that there are amplitudes, at loop level, there are amplitudes in the self-dual sector of gravity. We're going to meet them again very, very shortly. But their collinear behavior is not modified. So they don't see this one loop correction. You really do need to go to a first order deformation to see this correction, which is why I wanted to emphasize this role of first order deformations a couple of slides ago. So that correction to the holomorphic collinear singularity is captured by this diagram. At least this is the leading singularity. This is the thing responsible for the double pole. So we get one simple pole from the loop integration and one simple pole from the propagator going on shell. This kind of off-shell triangle diagram is captured by what's called the effective graviton vertex, which takes this form. I should say we don't usually think about a 3-point all plus amplitude in gravity because it's 0, or at least it's distributional at the very least. The reason that we're thinking about it here is because this leg that connects into this cross dot represents the rest of the diagram. This leg is off shell. This leg is off shell. So this triangle can be non-vanishing. And this is what it gives. You can see there's, in terms of the angle variables, there's going to be a simple pole there, but then we need to incorporate the propagator as well. So if we do that, we get what I like to call a holomorphic splitting amplitude, which takes this form. And we can check that it's consistent with this fact that in the true limit, where we take the momentum P2 to become fully linear, collinear with the momentum P1, this vanishes. So that corresponds to taking square brackets to 0 at the same rate at which we take the angle brackets to 0. And the fourth power beats the quadratic power. And so we indeed get the expected result. So to determine what deformation we'd expect, this one loop splitting amplitude to the correction it would give in the celestial chiral algebra, we use these hard generating functions, which I introduced a few slides ago. And the correction takes this form. There are also some subleading simple poles. These are a bit more subtle. They correspond to other possible one loop corrections, but this is the leading one. And then if we recast this in our sort of inhomogeneous coordinates and in terms of soft modes, what we get is we get precisely, I mean, I've written it slightly different here. It's a slightly more general formula. This isn't just for one of the APEs. This gives all of the leading double poles in the chiral algebra. But this is precisely what we got before. And again, we get this absolutely crucial factor of 2/5 pi squared, which I emphasized before. So in this direction, we're getting this factor by doing loop computations in gravity. And before I got that from, well, I guess I got it from a twistor diagram computation, which secretly are encoding the same information. Later, we can also see it from just requiring consistency of the chiral algebra. So we'll also be able to see it, just get it by thinking of purely abstract arguments, that this really has to be 2 over 5 pi squared. Yeah, I introduced this object R4. It's got some very complicated formula, but all it's doing is it's just acting as an SLTC intertwiner. Basically, it's intertwining the right-handed rotations. Yeah, so I really want to emphasize that this 1, 2 to the power 4 over angle brackets squared, that really is exactly the same structure I had on an earlier slide. So the 4 here is the fact that we get a square bracket to the power 4, and the 1 over z squared is exactly the 1 over 2 angle bracket squared. So you can really directly translate these singularities and amplitudes into structure constants of an algebra. Okay. Well, I say structure constants of an algebra. Unfortunately, these OPEs that this correction gives you, they're not consistent. You can a vertex algebra should have an associative product. That's sort of the analog of the Jacobi identity for a vertex algebra. It's the following identity, where these operators are operators in the vertex algebra. And of course, to do this, I'm using the standard equivalence of contours. And it turns out if I take these operators to be these particular operators, so just some of these W generators with an extra factor of Z to pick out the double pole, that this associativity condition tells me that the tilde W state 0, 0 has to vanish. Now you might think, well, maybe that's not catastrophic, this W tilde thing. It's actually central. If you go back and look at the tree level computation, it was a central term. Maybe I can just throw it away from the algebra. Maybe it's harmless to get rid of it. Well, unfortunately, this is just sort of the first of a tower of associativity failures. So if you throw that one away, I go one higher, I replace this W30 generator with a W40 generator. I do exactly the same computation, and now I find a non-central generator has to vanish. So you see that this really is catastrophic. This is total disaster. Okay, what on earth is going wrong? Well, those of you who were at yesterday's talk might be able to preempt what was going wrong. There's an anomaly in the twistor description of the theory. And so the existence of this chiral algebra, when we get it from a defect, it really relies on us having this twistor description. And it turns out that twistor description has a gauge anomaly. So it just completely fails to exist. And in 6 real dimensions, perturbative anomalies come from box diagrams, just like in 4 real dimensions, anomalies come from triangles. And it's precisely this box, which is the source of the issue. On space-time, this isn't an anomaly at all. There's nothing wrong with self-dual Einstein gravity as a perturbative quantum field theory on space-time. It's non-anomalous. What this corresponds to on space-time is the one loop plus amplitude. And what this is telling us is that although self-dual gravity exists as a perturbative quantum field theory on space-time, it's not a quantum integrable theory on space-time. So we should think of this gauge anomaly on twistor space as being a global anomaly in integrability on space-time. And we saw evidence of that, right? I mean, we saw explicitly on the previous slide that the hidden symmetry algebra, when one loop corrected, just fails to be associative. So you had a classical symmetry, which doesn't survive at the quantum level. It's just that classical symmetry is an infinite dimensional hidden symmetry. I also, when making the connection to celestial holography, I said that we should think of this hidden symmetry algebra as telling us about the universal collinear singularities of amplitudes in first order deformations of self-dual gravity. Well, interpreting this box diagram as the one loop plus amplitude, it's possible to see that if you've got these non-vanishing amplitudes in the self-dual sector, then the collinear singularities of amplitudes in first order deformations are not universal. So for example, if we do this first order deformation away from the self-dual sector to full Einstein gravity, that introduces this vertex, which can sort of have 2 minuses shooting out of it, which I wasn't allowed to write down in just the self-dual theory. And now that can feed into this non-vanishing box diagram in the self-dual sector. So if I take the momentum on this positive velocity graviton and on this negative velocity graviton, and I take them to become holomorphically collinear, then this diagram gets a singularity when this propagator blows up, the one that connects to the between the operator and the box. And that singularity depends on the deformation that I've done. And so there are no universal, the colinear singularities are not universal. They depend on what deformation I do, and I don't get a consistent chiral algebra describing. Well, it's then clear how to fix the problem. We just need to cancel the one loop all plus amplitudes in self-dual gravity. There are a few different ways of doing it. One way is to couple to scalars, fermions, gauge bosons, gravitinos in such a way that if you count the degrees of freedom in the theory weighted by their parity, you get 0. So there are some obvious examples where this happens. Self-dual supergravity, there's always going to be basically the total degrees of freedom weighted by parity would be 0. Fermionic degrees of freedom equal bosonic degrees of freedom in a supersymmetric theory. It also works in kind of a regularized sense in something called chiral high spin gravity, where you add infinitely many high spins. But these are exceptional examples. This is not a very strong constraint on a theory. I mean, it's very easy to write down a whole bunch of things that have this property. Yeah, I mean, you could, for example, take self-dual gravity and couple to an ordinary Weyl fermion, spin half Weyl fermion. That's going to be anomaly free. It doesn't need to be a gravitino, so not supersymmetric. A slightly stranger way of cancelling the anomaly is to couple to an exotic fourth order gravitational axion. And that's going to cancel the anomaly by a kind of Green-Schwarz mechanism. And that's the one I'm going to focus on now. In view of the time, I mean, there's a little bit more I want to say about curve background, so I won't go through this slide in too much detail. Here I'm just writing down what this extra degree of freedom looks like on twistor space. It takes this rather unusual form on twistor space. It's not really clear where this comes from, I think, unless you, if you go and look at what the anomaly co-cycle looks like, so the BRST variation of that box diagram on twistor space, it's not so hard to see that this is the kind of coupling that you want. And then this kinetic term is a little odd. People really came to these kind of kinetic terms by thinking about Kodaira-Spencer gravity. This is a kind of linearization of the closed sector of the B model topological string. And that's why it has this slightly exotic form. But when you take this down to space-time, it just becomes a fourth order scalar. But there's a sort of crucial difference in gravity as compared to gauge theory, which is that, of course, all fields couple to gravity. I mean, and in particular, this fourth order scalar through its kinetic term is going to couple to gravity. And that means it can contribute to the one loop all plus amplitude, and indeed this object contributes to the anomaly. In fact, it makes the anomaly worse if we ignore this extra coupling that we've added, this mu-dependent coupling. And then it has this axion type coupling. So it's coupling to the Pontryagin class. So this is a kind of fourth order gravitational axion. And there's this exchange diagram, which can be used to cancel the anomaly. And you find that the coupling constant needs to be tuned to a particular value. And this really works. I mean, the box diagram is going to give you a trace of x to the fourth. This exchange diagram is going to give you a trace of something squared. And fortunately, the indices on these things are SL2 indices, so we can always, this works, and these diagrams can cancel against one another, which is rather cute. I don't have time to talk about this in any great detail, but what you can do is you can couple self-dual gravity to self-dual Yang-Mills. That's a very natural thing to do. And now the coupled theory has a description. It has a bunch of twistor anomalies. It doesn't just have gravitational twistorial anomaly of the type that I discussed here. It also has a gauge twistorial anomaly, like I discussed yesterday, and it also has a mixed anomaly. And so it's very natural to ask, can we cancel all of these anomalies simultaneously with a single axion, which is both a gravitational and a gauge axion? So that's a priori, you wouldn't expect that to be possible because we've got 3 things to cancel and we've only got 2 coupling constants, the gauge and gravitational couplings. You wouldn't expect that necessarily to be possible. But remarkably, this cancellation works in all of the examples that it works in the gauge case. So for the gauge groups, SU2, SU3, SO8, and all the exceptional Lie groups, this cancellation works. And this relies on a particular normalization of the trace identity in these Lie algebras. So it's kind of this remarkable fact. Somehow the Lie algebra theory knows about this cancellation or something like that's going on. But yeah, so further details are in my paper with Dave and Atul on that cancellation. So now that we've cancelled the twistorial anomaly, we should expect that this theory of self-dual gravity coupled to a fourth order gravitational axiom has a consistent chiral algebra governing the collinear singularities of amplitudes in its first order deformations, and the associativity failure I mentioned before should no longer be present. And a very careful calculation shows that that is indeed the case, but you need to be, this computation is not, you need to be very, very careful when doing it, because we also need to think about the ways in which the axion OPs could be quantum corrected. So I think it's a fairly technical process, but what you find is that the cancellation works, and a cancellation works factor of 2 over 5 pi squared is 2 over 5 pi squared. And in fact, we could use this to bootstrap that coefficient. We could use this argument to determine it. And it's gratifying that it matches the one that people get by thinking about amplitudes. And so in conclusion, in this theory and in those other theories that I gave you, methods I gave of cancelling the anomaly, we get a kind of quantum group for self-dual gravity coupled to some extra fields which are required to cancel the anomaly. And you should think of this quantum group as being analogous to the Yangian for the principal chiral model, just it's a quantum group for something gravitational in 4 dimensions. Okay, I guess we're coming to the end. We don't have that much more time, but I want to briefly talk about curve background. So now I'm going to change direction, and I'm going to forget the quantum corrections that I've just been discussing, and I'm going to think about the classical hidden symmetry, but now on a curve background. I've already discussed the twistor formulation. I'm now going to imagine coupling to a very simple example of a holomorphic surface defect supported on the twistor line over the origin. It's just going to couple to this Lagrange multiplier field G. This factor of Z squared might seem a bit funny, but it's just there to give everything the right weight. Everything wants to live in the right bundle, and it's just there to make sure everything does. That's going to source the equation of motion of Poisson-BF theory with a delta function. And it turns out you can solve for this field H, which, if you remember, was the Hamiltonian for complex structure deformation. And so we can use it to determine the complex structure deformation, which now looks like this. So the way you think about this is we've taken some defect on twistor space and we've back reacted it. And what it's done is it's changed the complex structure on twistor space. And therefore, it's going to correspond and induce some kind of Hamiltonian complex structure deformation on twistor space. And that's going to correspond to some self-dual Ricci-flat metric on space-time. To find out what that is, we should find out what the curved twistor space is. So we can write down new coordinates, which are holomorphic with respect to this deformed D-bar operator. And you can show that these x alpha dot beta dots, where this is symmetric in alpha dot beta dot, are holomorphic. And I should say these are kind of overdetermined because these are the analog of the v coordinates, but we've got 3 of them because they're really quadratic in the v's. And so they obey a constraint, and the constraint they obey is this one, and we can recognize this. So this is actually Hitchin's description of the twistor space of the Iguchi-Hansen gravitational instanton, probably the simplest non-trivial example of a self-dual Ricci-flat background. Now, it's well known that in a Euclidean signature, the Iguchi-Hansen metric, it's got a singularity at the origin, which can be removed if you perform that Z2 quotient. So that's what I'm going to do, and I'm going to imagine that we really started. We started on the orbifold R4 mod Z2. We introduced this defect at the orbifold singularity. We back reacted, and when we did that, we resolved the orbifold singularity. And in fact, what's happened is that singular point has been replaced by a CP1, the instanton core. This is some kind of, this process of back reaction somehow resolves this Z2 singularity. I want to understand this hidden symmetry algebra on this curved background. And to do that, I mean, if we really want to think about amplitudes, it's natural to work in split signature, so we don't have to use complexified momenta. So I'm just, from now on, I'm going to work in split signature. There's another reason to work in split signature, which is the metric can be written in a slightly simpler form in split signature. It can be written in a Kerr-Shield form, which is much more convenient for computations. So to go from this curved twistor space to the space-time geometry, we just need to do what Penrose tells us to do. There's a sequence of steps we need to perform, and I'm not going to do them explicitly for you, but they're fairly standard. If you do that, you'll find that the resulting space-time metric takes this form. And again, sorry, these dotted circles maybe make this look a little bit more complicated than it really needs to be. These U alpha dots, U tilde alpha dots are just real coordinates. And this first term is really just a flat metric. It's just the flat metric written in split signature, plus, plus, minus, minus, written in this, written in terms of these funny coordinates. And then the entire deformation is captured by this term, which is very simple, very simple. And this form of the Yaguchi-Hansen metric was first discovered by Sparling and Todd in some work they did related to twistor theory. So we'd like to write down scattering states because we're interested in amplitudes. And we did this kind of funny Z2 quotient. And what that means is that our scattering states at infinity shouldn't be exponentials anymore. We don't want them to be e to the I p dot x. We really want them to be cosines. So they respect the symmetry x goes to minus x. It's very easy to write down twistor representatives of these states. They look a little bit strange. So they're just going to be something holomorphic on twistor space. Very easy to see that this is a natural holomorphic state on twistor space. I guess the funny thing is that there's a square root, but of course the square root's appearing inside a cosine. So when you expand out the cosine, there's only even powers, and that undoes the square roots for you. So this doesn't involve any branch cuts as it might first appear. And you can Penrose transform those states to get graviton wave functions here expressed through some kind of potential. And they take the following form. So these are exact scattering states on this curved background. And the result of doing this Z2 quotient is that our soft modes, which previously, if you remember, were labeled by two non-negative integers, they're now going to be required. Those non-negative integers are going to have to sum to something even. And that's the result of the Z2 quotient. So in the absence of the defects, I'm sorry, we are really running low on time, so I'll try not to keep you too long. In the absence of defects, if we set c equals to 0, then we know what the celestial chiral algebra should be. It should be the celestial chiral algebra on flat space, this L ham c squared I mentioned before. But we've now done this Z2 oberfolding, and so what we get is this Z2 fixed points. And that's where this sort of constraint that the sum of the M and N indices has to be even comes from in flat space. To determine what the deformed chiral algebra is, we need to do a computation. We can either do it on twistor space, where life is easy. We just demand BRST invariance of this state. So we take as inputs two scattering states, delta H1, delta H2, and then we build from them some product state that encodes the celestial APE, and we do that by demanding the BRST invariance of this object. Or equivalently on space-time, we take two graviton wave functions, delta theta 1, delta theta 2. We form this object, and we require that it's on shell. It obeys the self-true gravity equations of motion, so there's a typo there, which then determines some product state. And you can think of that as coming from the following diagram, which we've seen before, but now it's on a curved background. And it's really just like the position space version of the collinear singularity diagram I mentioned before. Working on twistor space, you can compute what the deformed algebra is. It's something complicated. In view of the time, I won't try and explain what's going on here. But crucially, we can recognize what this algebra is. So it's a certain scaling limit of what I'm going to call the loop algebras of some W mu algebras. And these W mu algebras are, again, very, very simple algebras. They're just the universal enveloping algebra of SL2C with Casimir fixed to mu. In fact, this is actually the algebra of angular momentum operators, not just their commutators, the full algebra you can get by writing down products of angular momentum operators if their total momentum is constrained to be, total angular momentum is constrained to be mu. So again, a remarkably simple algebra that we'll recognize, but maybe haven't thought of in this way before. Okay, you can do the same computation on space-time and you get exactly the same structure constants. This is working to first order in C squared because the space-time computation is orders of magnitude harder, and it's a formula like this encodes precisely the order C squared structure constant on the previous page. So we can get this from a space-time calculation. You can really see that this algebra is telling you about this algebraic with the structure and amplitudes from the curved background. Finally, I'm sorry I didn't get to this sooner because I know that there are members of the audience who are interested in non-commutativity. self-dual gravity, it's got a non-commutative deformation, which comes from replacing this Poisson bracket with a corresponding Moyle bracket. That has the effect of turning this at the level of the celestial chiral algebra, of turning this Lie algebra of Hamiltonian vector fields into the Weyl algebra. It just quantizes it. So we get the loop algebra of the Weyl algebra. This was shown by Dave, his student Simon, and their collaborator Wei Bu. And we can repeat all the computations I've done in the non-commutative setting. So we can try and deform the complex structure now in the non-commutative sense. We can still write down holomorphic coordinates. They're unchanged. But now what we find is that these holomorphic coordinates, if they were unconstrained, they generate the universal enveloping algebra of SL2. But in fact, there's this constraint, which when properly expressed in terms of the star product, gets shifted slightly. And this is telling us that the Casimir is being fixed to some value. And so what that's going to just get a scaling limit of this W mu algebra. We can get any of the W mu algebras by working with non-commutative self-dual gravity on the Seguchi-Hansen background. And there's this crucial shift of 3/16, which is needed for consistency with certain results known about Z2 invariant subspaces of Weyl algebras. And it's also consistent with this commutative limit. And one reason this is exciting is that you can get, there's sort of, when people first discovered this loop algebra of Hamiltonian vector field symmetry and gravity, or recently discovered it in the celestial holography literature, there was a natural question, which is, at that time, often people refer to as this the algebra of Hamiltonian vector fields, ham c squared, they refer to it as little w1 plus infinity. And it's very slightly different from little w1 plus infinity, but it's certainly very closely related. And one very natural question was, well, where does the capital W algebra deformation come from? And what this tells you is that the capital W algebras come from certain theories of non-commutative versions of self-dual gravity on these curved backgrounds. So it's a slightly complicated way of getting them, but they do arise in celestial holography. Okay, I apologize for going over time. I'll just, this is a short summary of everything I've said, but you've just heard it, and there's some future directions. So thank you very much.
Many thanks for wonderful talks.
That's okay. Yeah.